So I'd like to talk about this famous equation, probably the famous equation in science, E equals mc squared today. And this year is actually a big year for physicists. It's called the World Year of Physics. And that's because this is the year to commemorate 100 years since Einstein wrote several important papers in physics. And one of them really centered around this equation, E equals mc squared. So this is the guy we are celebrating about, Albert Einstein. And here's the famous equation, E equals mc squared. So I start talking about what this equation actually means. And I'd like to also tell you that much of the research we are still doing in physics and cosmology still center around this equation in many different ways. So I'd like to talk about those things as well. So looking at this equation, so what does it mean? Well, E stands for energy, M stands for mass, and c stands for speed of light. And as far as this talk is concerned, c is just a number, a big number. It's a really big number, but it's just a number. And then what this equation basically says then is that E is the same thing as mass, namely mass and energy are the same thing. And I would like to tell you that we understand energy quite well, but on the other hand, we don't understand mass very well. And that probably surprises many of you here, that we normally think that we understand mass. We know how much we weigh. We can put on the scale and measure how much we weigh. But we actually don't understand mass very well. We understand energy much better. So that's one of the things I would like to tell you today about. Okay, so here's the outline. I first talk about energy because I told you that we understand energy pretty well. And there are two kinds of energies, kinetic and potential. So I'd like to tell you about it. And then come to the mass. And this is actually a fascinating story, how things changed from the notion of mass back in the time of Newton to what Einstein told us based on his famous equation. And after Einstein, we learned that mass is actually a kind of energy. So that brings up a very naive question. What is this mass-energy thing? So I'd like to talk about that. And in addition to this puzzle, we don't understand what this mass is coming from. There are a lot of things we actually don't understand about the mass and energy in the universe too. So there's a big mass deficit in the universe I'd like to briefly talk about. And there's also some mysterious form of energy in the universe called dark energy. So this is the outline of my talk today. So let me begin with the energy. So as I said, there are two kinds of energies. So what is the energy to begin with? And energy means, in simple terms, it's the capability to do something. If you got energy, you can do something. For example, these people got a lot of energy. And as I said, there are two kinds of energies. If something is moving fast, that something got kinetic energy. If something is raised very high, that something got potential energy. And all kinds of energies we observed and studied in the laboratory are of either kind, kinetic or potential. So let's look at the kinetic energy first. So if something's moving fast, like Dash running like this, he got a lot of kinetic energy. And something more mundane compared to the superhero, like a racing car, of course it's running very fast, it got a lot of kinetic energy. And it has energy because it can do something like this. So that's what energy is about. And the other type of energy is the potential energy. And if you raise something really, really high up like that, then it can do a lot of damage. For example, if you cut one of the wires, it drops down, it probably destroys this building, maybe this guy gets crushed. So again, it can do all sorts of things. So something raised high has a lot of energy. So every kind of energies we see are of the kinetic kind or potential kind. But maybe you would say, well, I have heard of many other kinds of energies. What about those? Like thermal energy. And this is the kettle we have at home, and it's actually putting out steam. It's making the whistle blow, and of course the steam can even move a train like this one. So the thermal energy seems to be doing a lot of things. But it turns out thermal energy is just another kind of kinetic energy. And if you look at all the molecules that are making up a gas, and when a gas is cold, all the molecules are moving slow. But when the gas is hot, they are moving very fast. So thermal energy is actually just a kind of kinetic energy. These little things are moving fast, and that's what thermal energy is about. Then you may say, what about the chemical energy? And this is actually a picture of the birthday cake when my son became 13. And you see these candles lighting here. And what you see basically is that the wax is now burning and it's turning the energy into light. So there seems to be a lot of energy here, and that may also show up in a beautiful firework like this one. And it can also show up in something more destructive like this one for dynamite. So the chemical energy can do a lot of things. So what is it? Well, we know now that chemical energy is sort of a potential energy. And we know that in every atom we have in the universe, you have a nucleus inside and electrons are running around the nuclei. And when electrons sort of drop down closer to the nucleus, it's rotating about. So this one drops down closer, and then it can release the potential energy. So this is what the chemical energy is basically about. So all kinds of energies are either kinetic or potential. And another thing we know about energies is that they can transform from one kind to another. So if you watch, for example, the superhero pulling up this train, this is part of his training apparently, what's going on here is that he's transforming the chemical energy, which is the kind of potential energy from the food he eats. I don't claim to know biochemistry of a superhero, but presumably he eats too. So if he eats carb, that gets burned in his body, so that transforms the kinetic energy, chemical energy into something else. And in this case, he raises up this train, so that's the potential energy. So he's converting one kind of energy to another kind of energy. So that's the way energies work. They can do something, that's what energy is about, and they can transform from one kind to another. So that brings up this interesting question. So Einstein told us mass is kind of energy. So what is this mass energy thing? So if mass is another form of energy, what is it? Is it kinetic? Is it potential? And that seems like a reasonable question to ask. And it turns out we don't exactly know. So that's in some sense what the rest of the talk is about. Okay, so now we turn our attention to mass, and I'd like to briefly talk about the history, how things changed from the time of Newton to Einstein. So when we don't know something, then the first thing we always do these days is to look up Google. And I did that. And so I hit on the website from Encyclopedia Britannica. And this explains what mass is. In physics, quantitative measure of inertia. So this is what mass is. A fundamental property of all matter. It is in effect the resistance that a body of matter offers to a change in its speed or position upon the application of a force. The greater the mass of a body, the smaller the change produced by an applied force. So that's what the mass was about back in the time of Newton. So mass tells you how hard it is to change the course of an object. So that is more correctly called inertial mass. And we know this very well. If you're looking at something heavy, it's hard to move. And you can tell immediately which object has bigger inertia, right? So we can tell that right away. So that's what mass is about. And very important thing about mass, at least in those days of Newton, and it's to a great extent now too, is this. For years, it was assumed that the mass of a body always remained invariable. This notion, expressed as the theory of conservation of mass, held that the mass of an object or collection of objects never changes, no matter how the constituent parts rearrange themselves. We know this very well too. The conservation law of mass, you can see that in a situation like that. And if you sum up all the masses of individual cars, and before and after the accident, and after the accident, of course, you have to make sure that you pick up all the debris on the ground, and sum them all up. But then you find exactly the same number before and after the accident. So that's the conservation law of mass. That's a very familiar concept too. But then came the change due to Einstein. With the advent of the special theory of relativity by Einstein in 1905, so this is exactly 100 years ago, that's why we're celebrating it, the notion of mass underwent a radical revision. Mass lost its absoluteness. The mass of an object was seen to be equivalent to energy, to be interconvertible with energy. Mass was no longer considered constant or unchangeable. And to explain something this radical, I thought that it's nice to bring somebody who knows this subject very well, which means Einstein. So I brought Einstein here, and you can listen to him.
It follows from the special theory of relativity that and energy are both practical manifestations of the same thing. A somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal to mc squared, in which energy is first equal to mass multiplied with the square of the velocity of light, shows that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent. According to the formula mentioned above, this was demonstrated by Cockcroft and Walton in 1932 experiment.
Okay, so you listen to Einstein. This is his real voice, recorded way back. I don't know what year that was. But anyway, he gave a speech about his famous equation, E equals mc squared. And the emphasis is due to me. He basically said mass and energy were in fact equivalent. That's the essence of this equation. So he talked about the mass being convertible to energy, energy being convertible to mass, and also referred to this experiment by Cockcroft and Walton. So it's probably useful to look at what Cockcroft and Walton did in 1932. So this is what people call the first atom smasher. What they did, was to bring in protons, which is the nucleus of hydrogen atom, and hit the lithium atom very hard with it. And it turned out that this actually produced two helium atoms. So in some sense, this is a modern alchemy. You can change one type of chemical element to some other kinds of chemical element that way. And what they have seen is this. If you sum up the masses of the objects they had initially, namely this one, which weighed this much in certain unit, and this one that weighed this much in the same unit, so you add them up. On the other hand, it produced these two helium atoms in the end, so you know how much it weighs, so you can compare them. If you sum up the masses of the proton and lithium, you get one number. If you sum up the atoms, the helium atoms, you get some other number, and there's a difference. The mass, the total mass before the reaction is bigger than the total mass after the reaction by this much. And what happened here is that the part of mass got somehow released and got converted, in this case, the kinetic energy of these helium atoms. So after this reaction, these helium atoms just flew away with high speed because the mass got converted to their kinetic energy. So that's what they have seen. So indeed, this is the first sign that mass can be converted to energy. And of course, once mass can be converted to energy, you can convert energy to mass too, and that's what these people did. And this is a picture taken back in 1933, and probably this is the first picture of antimatter produced in the laboratory. And what they have done is send in light. And light has energy. So they send in energy here, and that energy got converted to a matter particle, electron, an antimatter particle called positron. And of course they have mass. Electron has a mass, positron has the same mass as the electron. So what happened here is that you send in energy, and energy got converted to mass. So the mass can convert to energy, and energy can convert to mass. Now you can see that they are in fact the same thing. Just like the chemical energy, potential energy, kinetic energy, they were all the same thing. They are energy of one kind that can get converted to other kinds. The mass is also just yet another kind of energy that can be converted to kinetic energy and potential energy and so on. So this was a great discovery back in 30s. And these days, even though this sounds sort of the science fiction-like, we can actually produce antimatter in some quantity and use that all the time. This is an experiment done in the laboratory where you send in matter and antimatter from both directions, and they actually annihilate into pure energy in the middle. And that pure energy got converted to other forms of matter and antimatter in the laboratory, and you see the sprays of particles coming out this way. So you can really use antimatter now to convert mass to energy, and energy can get further converted back to mass of other kinds. And this is in some sense routine for many of the physicists working here. And antimatter, certainly does sound like science fiction, and it does show up in many fictions indeed. And in this episode of Star Trek, they are transporting a bulk of antimatter. And as you probably know, the spaceship's actually powered by antimatter in Star Trek stories. And some amount of antimatter got stolen, so they have to actually track it down. And this is a very difficult business as far as I can tell, because if the minute you touch antimatter, then you basically blow yourself up. You get converted to pure energy. Your mass, and touching antimatter, you become energy. So you have to be incredibly careful not to touch it, and especially when you try to steal it, that's a very hard moment to be careful about. And this is a more recent book by Dan Brown, which he wrote before he wrote his famous Da Vinci Code. And in his story, Vatican is actually threatened to be blown up by only a 1/4 gram of antimatter in a little canister sitting in the basement. And if you do the math, you can actually really see that, because this c squared, speed of light squared, is such a big number. Just a little bit of mass can give you a huge amount of energy. So this just a 1/4 gram of antimatter, like something like that, can really blow up a whole building if you can really convert that to pure energy. But that sounds all like science fiction. So is there something more mundane we actually see on a daily basis, that energy can get converted to mass and mass can get converted to energy? And there is. So this is the famous example, the sun. And people did ask the question, how does the sun shine? Because we are getting a lot of energies from the sun. So where does that whole energy come from? And in 19th century, there were two competing ideas about how old the sun was. Lord Kelvin, probably he was the most famous and trusted physicist back then, said, well, knowing only chemical energy, which was the most powerful source of energy back then, he estimated that sun cannot be older than 30 million years. Within 30 million years, sun would use up all of its energy, so it can't be older than that. But that actually conflicted with various records in geology, and then also, if you think of evolution, the Darwin also objected to this idea, and the geologists estimated that the Earth is as old as 4.4 billion years. And we don't believe that Earth is older than the sun, so that seems to bring up a big contradiction here. And the resolution turned out to be that the physicists were wrong. We have been wrong many times. So the way the sun is producing energy is by converting a little bit of its mass to energy. So this is how it works. You bring in 4 nuclei of hydrogen atoms, namely protons together, and that get converted to a helium atom and 2 antimatter particle positrons, neutrinos, and releases quite a bit of energy this way. And the way it works is the same story. You sum up the mass of the objects you had initially, that's 4 times the mass of the protons, and then you build up the helium, and you find that the mass of the whole object you have at the end of the reaction is less than the mass of the objects you started with. So that means that you have released some of the mass energy into pure energy, so that comes out in the form of heat, light, and also neutrinos. So fusion of these protons happening in the sun releases a lot of energy. So if there weren't for E equal mc squared, we actually can't live. Our life depends on this equation where the sun is doing the job to convert part of its mass to energy. And of course, this is happening at the very core of the sun. It looks like this is something you can never test. But it turns out, recently we have found the final proof that this is indeed what's going on in the core of the sun. So it turns out there are some particles called neutrinos that are produced in this reaction here that are streaming through the sun and without much hindrance. The neutrinos are very shy particles, so they can get through any kind of matter very easily. And as a matter of fact, as we speak, there's something like tens of trillions of neutrinos going through your body every second. Does anybody feel them? Nobody? When I asked this question in a class, actually 2 students raised their hand. No? Okay. All right. So anyway, so these neutrinos are streaming out of the sun all the time because this fusion reaction is happening in the core. And people have actually detected those. They are very ghost-like particles because they are so shy. But if you build something really big, like this tank of 50 kiloton of water underground, you sometimes see them. So people actually managed to take a picture of the sun using these ghost-like neutrinos, like that. So this picture was taken with neutrinos in pitch darkness, 3,000 feet underground. No light but they detected neutrinos coming from the sun, and this is the picture of the sun. So now we have the final proof that indeed this is what's going on in the sun, so we live based on E equals mc squared. So this equation turned out to be very important for our existence. Okay, but now that we have heard that mass and energy are the same thing, that brings up a very naive question. What is this mass-energy thing? You know, if you're talking about kinetic energy, you can picture where the energy is. Something is moving. If you're talking about potential energy, again, you can picture what the energy is. Something is raised very high. But if you say something sitting here, just mass, got energy, you would wonder, where is that coming from? What is this mass energy thing? And that actually turned out to be a pretty difficult question to answer. We have answers to part of the question. I'll tell you that part. But we don't have the answer to the whole question yet. So that's what everybody is interested in finding out, especially in the physics division of this laboratory. So thinking about what the mass energy actually is. If you think about the much of mass we are made of, so if we put ourselves on a scale, we measure how much we weigh, and most of that mass is actually in the atomic nuclei made up of protons and neutrons. And we have now a pretty good idea on what that mass energy is coming from. So protons and neutrons turned out to be made of these quarks. And they are confined in such a tiny space, and they are moving around very, very fast. So they are moving feverishly inside this very tiny space of protons and neutrons. So it turns out the proton has energy, even though the proton as a whole is at rest, it's not moving, but things inside are moving so fast that that gives you kinetic energy. So when you actually put yourself on a scale and measure how much you weigh, what you're actually measuring is how much these quarks inside protons and neutrons are moving. So that's where most of our mass is actually coming from. And Murray-Gell-Mann first proposed this idea that protons and neutrons actually made up of these quarks living inside. But it turns out it was a very hard theory to test, because you can never take a quark out of a proton and neutron and study them, on their own. So they are actually sort of sentenced to life in prison. And this had been understood much later by these gentlemen, Gross, Polz, and Wilczek, who received Nobel Prize last year. What they have told us is that the kind of force that binds these quarks together becomes much, much stronger as you try to separate them more and more. So if you try to pick one quark out of the proton, try to observe it outside it, then as you try to pull it, and the pull becomes harder and harder, and at some point you have to give up. You can't do that anymore. So they are sentenced to life in prison. You can never take them out of a proton and neutron in isolation. But nonetheless, this is the way the protons and neutrons are made. Then that is how what's giving us how much we actually weigh. But we could actually study those quarks in great detail, again by using the annihilation of matter and antimatter. So you're converting energy again into mass, so you're producing these quarks. And it turns out you can produce a quark and its antimatter counterpart, anti-quark, from the pure energy. You can do that. And then quark wants to separate away from the anti-quark in the laboratory. But once they become farther and farther apart, at some point quark realizes, oops, I was supposed to be in life in prison. I have to actually build a prison around me. So that's actually what a quark does. Quark starts to build a prison around it. And that still shows some leftover, and the leftover still needs to dress itself with a prison around it, and so on. So at the end of the day, you start producing a bunch of particles this way, and that's what you observe in an experiment like this. So you have produced a pair of quark and anti-quark. You can study them in great detail, but when you see them, they're always dressed up in their own little prisons, and that's what we see in this picture. So we know that indeed the quarks exist, and that's how we are made of, and their motion is where most of our mass is coming from. So that's good. We now understand much of the mass of ourselves. Our body, namely atoms, is made of protons, neutrons, and electrons, and most of the mass of proton neutrons actually come from the feverish motion of the quarks that are confined eternally within. So that's what's going on. So that's a good story, but that still leaves questions. There are other things we know, like electrons that are moving around in atoms, and they got mass too. But that's kind of strange. If you pick an electron and look at it, it's just a point. It doesn't seem to have anything inside. So how can anything that doesn't have anything inside have energy when it's at rest. And we got so much used to the fact that everything we see have mass. But if you think about it, it's actually kind of strange. Something that doesn't seem to have any structure in it, that doesn't seem to have anything in it, anything moving inside, still got energy. So where does that come from? And that actually turned out to be a big mystery, and we don't know the answer to that yet. But I can tell you what the theory is at this moment. But anyway, so the most of mass of a body now is understood by the motion of quarks, but we don't understand where the mass of individual quarks actually come from and where the mass of the electron is coming from either. And if you just imagine turning off the mass of the electron, you know, your body would disintegrate in nanoseconds. Electrons would fly away from your individual atoms, and your body's gone. So it's important to keep the mass of the electron somehow. So we got to understand where it's coming from. So this is the question. This is the theory, which is very bizarre. So what this theory says is that we are dipped in what I call the dark field. The whole universe is filled with this dark field. And everywhere you go in the universe is filled with this dark field. And this dark field is dark. It doesn't disturb light. So when light wants to go through the universe, it can just keep going. And that's how we can still observe very distant stars and quasars and so on. So that's okay. But when you put an electron in this universe, it starts bumping on this dark field. And it gets bounced around like this. That means it doesn't go very far. And if something doesn't go very far, then it doesn't go with speed of light either, which means that electron actually acquired a mass. Somehow this bumping gives energy to the electron. And if you look at some even heavier objects, there's actually something similar to electron called muon. It bumps on this dark field more often, and it gets more mass, namely more energy. And heaviest particle people have discovered, and people in the physics division played a major role in this, is a quark named top quark. And this one is very heavy. And this one should be bumping on this dark field all the time so that it gets a lot of energy from this bumping. So this dark field that's filling up a universe is giving energy to all of these elementary particles. But we just don't know what it is. It is supposed to be here, right here, so that your electrons in your body don't fly away. It's important for you, but somehow we don't know what it is. So that's why we are trying to find out what this dark field actually is. So the idea is that this dark field is supposed to be everywhere in a universe. So if you can pump in enough energy, you can knock it out and observe it. So that's the idea called Large Hadron Collider. And this is a huge facility. What you see in this picture is the Geneva airport. This is the runway. And people have built a tunnel which is this big. And this whole tunnel is now being instrumented by a lot of the pipes and the magnets and so on. And if you build something big, you can make the particles very, very fast. It's like a little swing, which maybe cowboys used back in those days, that if you have a little sling and if you spin it around, if the string is not very long, it doesn't spin too fast. But if you have something very long string, then the object would move around very fast. In a similar way, if you build something very big, you can make the particles move very, very fast, very close to the speed of light, and they actually can scatter with each other. And that means you're pumping a lot of energy into empty space. And because this empty space is supposed to be filled with this dark field thing, you should be able to knock it out and observe it. And to observe it, you need to, again, build a big instrument like this one. And that's the experiment many people here are involved in called ATLAS. And this thing is also huge. This instrument itself is something like 5 stories high. And using this huge facility and this big instrument, you hope to see what is actually stuck right here in a universe and is disturbing the motion of all these particles. So that's the way we try to find things out. So hopefully we would understand where this mass energy is coming from by doing these things. But that probably wouldn't be the whole story about mass and energy. When you think about mass, we learn it's a kind of energy. But again, you can ask a naive question. Is the whole mass of the universe made up of things we know? It turns out that's not the case. and there's some mass deficit going on in our universe. So there's something called dark matter. We talked about dark field. Now we're talking about dark matter here. And there are many evidences that the dark matter should exist, which is not the kind of things we are made of. If you just observe this magnificent swirl of the galaxy, you can look in a telescope, you can actually see how much light there is. And that you can tell, and from that you can tell how much mass there is in the form of stars. But it turns out, if you look at the edge of the galaxy, it's actually spinning pretty fast. Our solar system is also moving around in our own galaxy, and is actually moving pretty fast. It's actually about thousands of speed of light. We're moving actually pretty fast inside our own galaxy. And if you look at any other galaxies, the edge of the galaxy is always moving pretty fast, so fast that if the all source of gravity that is putting the galaxy together is coming from the whole mass of stars combined, there isn't enough. The galaxy is supposed to be flying apart. But what we see is the galaxy sort of stays put. It doesn't fly apart. It stays rotating around for many, many billions of years. So something is holding the galaxy together. So galaxy is actually held together by mass far bigger than all stars combined. So we can come up with numbers that way. And this is a pie chart. And I still can't forget the first time I used this kind of pie chart, and I gave a talk in actual physics department down the hill. And I saw sort of puzzled look among the audience. And I knew the reason. Physicists don't use pie charts. But the only time we actually see pie charts is when we talk about money. So that actually explained to me sort of the painful look among senior members of faculty. They must have been thinking that now that I'm staring at a pie chart, there must be a budget problem. And that's indeed what's going on in our universe. There's a budget problem. There are kinds of energies and mass that are not accounted for. I spoke of dark matter, and I can come to dark energy next. But it turns out most of mass in our universe is not accounted for. The kind of mass we know of, namely atoms, is only this much in this pie chart. This is dark matter, and we don't know what it is. It's not accounted for. And this is dark energy. We have even less clues on what it is. So there are things that are not accounted for in the budget sheet of a universe, and that will certainly worry people like him, right? So we got to find out. So the first thing people thought was that if there's some kind of mass that's missing in a universe, there must be some kind of stars, obviously. There must be some kind of stars. They're just too dim that we can't observe them. But it turns out you could actually look for such dim stars. And they were called machos, and this field is filled with all these funny acronyms. Machos actually stand for massive compact halo objects. So they are supposed to be sort of dim stars you can't really see in telescopes, but they are moving around in a galaxy and holding galaxy together. So that was the idea. It turns out you could actually look for these dim objects, and the way you do it is to keep observing some of these distant stars, in this case Large Magellanic Cloud. And once in a while, every once in a while, if there are those dim stars flying about in a galaxy, they may pass exactly along the line of sight towards one of these stars we are constantly looking at. And once that happens, this is another thing Einstein told us, when some heavy object passes through the line of sight, the light actually gets bent. Because the mass and energy is the same thing, mass falls, light has energy, so energy falls too. That's what Einstein said. So light should fall if there is some massive thing out there. So it turns out if this kind of dim stars people talked about passes through the line of sight, that actually acts as a lens, and it magnifies the brightness of a star, and you can look for such a thing. And that way, people did find some examples of possibly a macho, that a macho actually passed through a line of sight towards one of these stars, and star suddenly brightens up and again fades and go back to the original brightness. So that kind of thing actually does seem to happen. But when you do the careful counting on how often this happens and how much mass there may be in the form of these dim stars in our galaxy, it just turned out that there's not enough of them. So our galaxy is held together by some invisible mass, but it's not stars, something else. So we have to change the ideas from machos now to WIMPs. And the WIMPs are supposed to be wimpy, so they're like neutrinos, they're ghost-like, they're passing through your body all the time, but you don't feel them. So the whole Earth is actually being passed through by the WIMPs all the time. The WIMPs are holding galaxy together, it has mass and floating in a galaxy, but we don't feel them. So that's the idea now. So the WIMP actually stands for something, weakly interacting massive particle. And so this weakly interacting massive particle is floating in a galaxy and has enough mass to hold it together. So that's the idea. So how can you actually expect such a massive particle in a galaxy? So here's the idea. When the universe started with a hot Big Bang, it was so hot that there was a lot of thermal energy. When we talked about this, thermal energy is that the particles just moving very fast and they got a lot of kinetic energy. So in the early universe, the universe had a lot of kinetic energy in it. And when there was enough energy, then energy can be converted to mass. So these heavy massive objects could have been produced in such early stage of the universe when it was very, very hot. So once they are produced, and assuming they don't decay away into something else, they got left over from this fiery Big Bang, and they may still be floating around now. So that's the idea. So the dark matter, which may be made of these WIMPs, are actually left over from the Big Bang. But even though they are so wimpy, we still try to look for them. And this is, again, the idea how you might do an experiment. You go to some quiet environment, like underground in a deep mine, and so not a lot of activities going on, so you get shielded from all kinds of other disturbances. And you place a detector which is incredibly sensitive. And what you do is sit there and wait, and wait, and wait. So if the dark matter particle comes in, it's so shy that it can very easily sneak into this underground location. But again, just like neutrinos did, once in a while, they may produce a little kick in your sensitive detector. And that's what you're waiting to see. Certainly it doesn't happen very often, but you don't want to miss it when it happens. So you really wait, but not just keep waiting. You wait very carefully and intensely and eagerly not to miss this little kick that may be produced by the interaction of the dark matter particle. An actual experiment actually looks like this. And this is actually a huge cryogenic system. And in this cryogenic system, you have very sensitive detector in it. And that way, they are waiting for this little kick by the dark matter particle sneaking into this underground location and produce a little bit of energy deposit in this detector. So this is one way for looking for dark matter particle, where this lab also has been having some involvement. And another way to look for dark matter particle, WIMPs, is this. We got pretty big mass around us, which is the sun. So when these WIMPs, come close to the sun, they may get trapped because the sun got big gravity. So maybe they get trapped and they start sinking to the bottom. But of course, the sun doesn't have a bottom. In this case, the bottom means the center of the sun. So the trapped dark matter particles may sink all the way to the center, and then maybe they start meeting each other, and they would annihilate with each other. Just like matter and antimatter can annihilate and become pure energy, they may also annihilate and produce a lot of energy in the core of the sun. And some of those energies are likely to become neutrinos in the end. And as we have already talked about, neutrinos can get out of the sun very easily. So these neutrinos produced from the annihilation of dark matter might actually come out from the sun, and we could look for them too. But this happens even more rarely than the kind of experiment I talked about. So you need an experiment which is even bigger. So even bigger, as big as the ice in Antarctica. That's the experiment called Ice Cube people are building. And this is an idea to actually make this whole ice of the Antarctic an experiment. And they have been deploying these strings with many sensitive detectors called photomultipliers all the way down to almost 2.5 kilometers beneath the surface. And this thing is 1 kilometer wide, 1 kilometer thick, and 1 kilometer tall. This is a huge experiment. And once you have something this huge, you may be able to actually detect neutrinos coming from the center of the sun. An actual location looks like this. It doesn't look very warm. But here, what you can do is to actually drill a hole into this 3 kilometer sheet of ice just by flushing a lot of hot water. So you boil water and you flush it against the ice, and that way you can just keep drilling all the way down to the bottom. And it stays unfrozen for about a day, I was told. So within a day, you have to make sure that you do all the work you were supposed to do, and then it starts freezing again. So you can never touch it probably for the rest of your life. So you have to be careful to do the things within this available day when the ice is not frozen. But that way, they are trying to instrument this whole volume of ice and turn them into an experiment. So this is the way you may actually see that there is indeed WIMPs floating around in a galaxy, and they are pulling the galaxy together. But that way, we still don't quite understand what this dark matter actually is. And in order to really understand what this dark matter thing actually is, you would like to study them in the laboratory, and you hope to actually produce them at an experiment where we talked about actually knocking out something out of the dark field. Once you can pump enough energy into space, you can create massive objects, just like it was done in the early universe. So hopefully, we can actually produce this dark matter particle in a laboratory too. And if you can do that, you can study them in great detail and understand their properties. And of course, you're looking for something invisible. So how do you do that? Well, this is the way you might do it. You again have this big collision of energetic particles. In this case, we're talking about 2 protons together. And it has a lot of energy in it, and it produces a lot of particles coming out of this collision. But once in a while, you might see a collision event like this one. So this particular collision of 2 protons may have produced a bunch of particles, but only going this direction, but none going that direction. And that's strange. We know the energy and momentum are conserved. If something's produced that way, everything should be balanced. Something else should be going that way too. But now we can tell that something is something we don't see. So what we are doing is actually to see an invisible particle. We don't quite see it, but the fact that everything doesn't seem to balance together means something is going this way that is invisible. So that becomes a very good candidate for dark matter particle. Something is produced in your experiment that's heavy, but you don't see it. So you would like to study the property of the dark matter particle that way. And if you really try to understand the property of this particle, you probably want to have yet another kind of experiment. And that is another thing the people in this division are involved with, called linear collider. In this case, what they're trying to do is to build a long section instead of a ring, like the picture you saw before, and accelerate electrons and positrons head-on and let them annihilate in the middle. And when they annihilate, they become pure energy, and again, they can be converted to other forms of mass in the experiment. And when I first heard of this idea, I thought it was really crazy. Because what you're supposed to do in this experiment is you accelerate the beam of electrons over something like 10 miles, and then you focus them down to a size of about nanometer, and you have to make sure that they meet each other from both ends. And I was told that you can do that. So that's what this experiment is about. It's a super high tech if that really works, and I'm still worried about this, but anyway. So once you do so, you can probably start really pinning down on the properties of this dark matter particle. So this is the grand hope we have. It may not work this well, but at least this is something we have a very good shot at. So how do we know what dark matter particle is? It is supposed to be right here, but we still don't know what it is. So we have seen some measurements from looking at the stars and galaxies that told us how much dark matter there should be. We also talked about these experiments underground looking for dark matter giving you some reaction in your experiment. So that they are called detection experiments. And we hope to also produce these dark matter particles in these big experimental facilities and understand the properties in great detail. So what we hope to see is that the properties you measure in the laboratory, once you can produce these dark matter particles in quantity, would explain how often you actually see those particles in those underground experiments and how much that got left over from the Big Bang. And if you can really explain these measurements coming from the stars and galaxies and these underground experiments using the properties we measured in a particle accelerator experiments, then we can finally claim a victory. We can finally say we understood what dark matter particle actually is. And that in turn brings up our understanding of the universe all the way then when the universe was only about a tenth of a nanosecond old. And because the universe started with a Big Bang, it was very hot at the beginning. And this dark matter particle, being heavy, must have been produced when the universe was very hot, which means the universe was very young when those dark matter particles got produced. And the rest of the universe, the rest of the time, the universe kept getting bigger and bigger and also became colder and colder. Eventually, it started to form atoms, it started to form stars and galaxies, and this is you. So this is where we are. And right now, our understanding what happened at the beginning of the universe is limited to about here when the nuclei, atomic nuclei started to form. That's when the universe was about a second old. We don't know what happened in the universe earlier than this point, at least right now. But if we can really understand the properties of dark matter by combining these different measurements, including particle accelerators, we will be able to understand how the universe was when it was only about a tenth of nanosecond old. So that certainly would be a huge progress in understanding what the beginning of the universe was. So this is one of the sort of the hopes we have, trying to understand what the most of the mass in the universe is made of and how that relates to what happened in the early stage of our own universe. So that's so much about dark matter. And then I switch my gear to another mysterious thing called dark energy. So just a brief recap, that universe is expanding. And just thinking about how we know that universe is actually expanding, the way you actually know it is very similar to the Doppler effect of the approaching ambulance. So when you see an ambulance coming towards you, and this is my son actually, dressed as Einstein on a Halloween night. And when the ambulance is approaching you, then pitch of the siren sounds high. And we all know that when it's actually moving away from you, then the pitch actually gets low. So the pitch is high here when it's approaching, pitch is low when it is moving away from you. And when you look at the distant stars, you do the same thing. If you see a star, the star may be supposed to be yellow. But if the star is moving away from you, it actually looks redder. So this difference in color is telling you how fast the star is moving away from you. So this is exactly the same idea as the moving ambulance. And by looking at these distant stars, people had figured that they are actually moving away from you. All of the stars are moving away from you. What it means is that it's not that the individual stars or individual galaxies are moving in some funny way, that they know where you are and trying to move away as far as possible from you. It's not that. What is going on here is that the whole universe itself, the space itself, is expanding. So imagine that the universe is sort of like grid. And all these galaxies are put on a certain grid points. Just picture that. And what's going on here is that whole grid is actually getting bigger. The individual galaxies are not getting bigger. The grid is getting bigger. But if you are here in this galaxy, and suppose you're looking at that galaxy over there, and as time goes on, you'll find that this galaxy is now farther away. Because the space is getting bigger, all of the galaxies around you look like they are moving away from you. So that's what's going on. So the universe is getting bigger and bigger. It's getting more and more stretched. And as it gets bigger, it gets also colder. And so if you actually take the film of the universe and turn the film backwards, you find that the universe was smaller and smaller back then, and that means it was hotter and hotter. That's why we talk about Big Bang. That's how we actually know what the Big Bang happened, and so on. And of course, this may just look like a story, but you can actually see the afterglow of the Big Bang. And this is the result from the COVID satellite, where people in this division had been also involved in the past. And what they observed, for example, here, is that we are actually living in a microwave oven. The universe is filled with microwave. It's kind of radio. And this radio is actually the afterglow of the fiery Big Bang that happened 10 billion years ago. And we are still seeing the afterglow of the Big Bang in the form of the microwave. So we actually know, very sure, that the Big Bang indeed happened. So we've been living in this expanding universe ever since. But what people discovered more recently is even more strange thing about this, that the expansion of the universe is actually getting faster, accelerating universe. And this is another thing Einstein told us. The expansion of the universe goes with how much energy there is in our universe. More energy there is, like when the universe is very hot, the universe expanded fast. More energy means faster expansion of the universe. But as the universe gets bigger and bigger, and if you think of, for example, mass, you have certain amount of mass in this volume of the universe. And if universe gets bigger, then universe gets more and more dilute. You have less and less stuff in your universe. And if you have less mass, again, Einstein told us, it's less energy. So universe is supposed to expand less fast, slower than what it used to do. So as the universe expands, universe becomes colder, more dilute, and it's supposed to slow down at the same time. That's how we've been thinking for many, many decades. But it turned out, by observing very distant stars called supernovae, people, especially in this division led by Saul Perlmutter, figured that universe is actually getting faster instead. And that's really strange. As universe gets bigger, something must be actually getting more energy than less energy, so that universe can get faster that way. And that's really strange. You need something that gains energy. It doesn't get more and more dilute, but becomes more and more energy as universe stretches it. So this is something we don't know what it is yet, but what we call dark energy. So this dark energy is supposed to be 70% of the energy in the universe. So the bulk of energy in the universe is actually dark energy. It is ripping the universe apart. The universe is getting faster and faster. And the way it does it is that it keeps getting more and more energy as the universe expands. And that sounds like a great story. That's an infinite source of energy. If that's true, Department of Energy has done a great service to the community, has found the infinite source of energy. The only little problem is that we don't know how to use this thing. But anyway, so it looks that way. Dark energy looks like an infinite source of energy, and we have very little clue what it is. So it looks very spooky to me. So in order to figure out what this dark energy is, again, we're not sitting still. We're trying to do something about it. And one experiment people here have been developing and proposed is an experiment called SNAP, by observing these distant supernovae in a greater detail than we have been able to do with telescopes. By launching a satellite like this one, we'll be able to understand the nature of dark energy much better. So one key measurement we would like to do about dark energy is this. I said, as universe gets stretched, dark energy gains more energy. So at least we would like to know how much energy it gains. Does it get a lot of energy, or maybe a little bit of energy as the universe expands? So we can tell that by measuring how exactly universe is getting faster and faster in its expansion. For example, one idea I actually liked about is that the dark energy may be some kind of walls. That you imagine these walls actually forming some kind of structure, and that's getting bigger and bigger. And actually wall gets more energy when you stretch it. It's like a sort of the sheet of bubble gum, and if you stretch it, you're pulling against force. So actually the bubblegum sheet gets more energy that way. So something like a wall gets more energy indeed when it gets stretched by the expansion of the universe. So it may be something like that. On the other hand, some other ideas, which actually Einstein himself came up with, is called the cosmological constant. And this one actually gets even more energy than these walls do. So by doing detailed measurements, you can try to tell them apart. And that's indeed what this experiment SNAP will be able to do. Okay, so I came to the last slide. We talked about this E equal mc squared, the most famous equation probably in science. It says the energy and mass are the same thing. I told you that we understand energy quite well, but we actually don't understand mass very well, which is kind of surprising. We talk about mass all the time. We talk about how much we weigh. We're always trying to shed weight in some way. But nonetheless, we actually don't quite understand where the mass energy is coming from. It turns out most of the mass of our body is coming from the feverish motion of quarks, which are alive in prison. They are confined eternally inside protons and neutrons, and their kinetic energy is giving us that mass. But the rest of the mass comes from this mysterious dark field. These particles are bumping on this dark field all the time and gets a little bit of energy from that. And we don't know yet what this dark field is made of. Most mass in the universe is not the kind of mass we know of. They are called dark matter. Again, we are trying to figure out what it is. And most energy in the universe is dark energy. We have less clue on what this thing is. But nonetheless, again, we are trying to understand what they are. So at least we don't know what they are yet, but we have strategies to figure these things out. And many experiments are now coming online and address these questions. So this is actually a very interesting time. So we can expect a major advance in these questions in this decade. Thank you for your attention.